Hello, and welcome to Paige's explanation of polar equations and graphs. My name is Paige, and I will be explaining polar equations and graphs. Let's get started. Polar equations! In a rectangular coordinate system, the graph of an equation y equals f of x consists of all points whose coordinates xy satisfy the equation. In the polar coordinate system, this is a different story, as points have infinitely many different pairs of polar coordinates, so that a given point may not have some polar coordinates that satisfy the equation r equals f of theta, and others that do not. Taking this into account, we define the graph of r equals f of theta in the polar coordinates to consist of all points with at least one pair of coordinates, r theta, that satisfy the equation. Let's take a break from all this thinking to look at some pictures of polar bears and polar ice caps. Okay, so for the most part, polar equations are always graphed from 0 to 2 pi. And there are 5 different kinds of polar equations. We have lines, a line, and then we have limicons, like lima beans. Next, we have lemniscates, then polar roses, and lastly, we have spirals. So the idea of this video is to help you remember what polar equations look like when they are graphed. So the most elementary way to graph the equation r equals f of theta in polar coordinates is to plot the points. So the idea of that is to choose some typical values of theta from like 0 to 2 pi, so like pi over 2 and pi over 4 and stuff. And then you calculate the corresponding r values by plugging the theta into the f of theta equation. And then you plot those pairs, r theta, into the corresponding polar coordinate system. So it is very simple, and I will show you. Alright, so we're going to start with lines, and they're the easiest thing to graph in the world, especially with polar. They're super simple. So, basically, an equation for a line in polar can be written in terms of theta, like theta equals pi over 4, which is basically just a line that crosses through the origin at 45 degrees, like pi over 4, you know? Just like that. But, you know, it can also be written in terms of r, but it's really, really easy to do that too. You just need to remember these conversion equations. So, x equals r times cosine of theta, and y equals r times sine of theta. So basically, if ever you're in a polar equation and you see cosine, it's probably going to have something to do with the x-axis of that graph, and y would be the sine. And then always remember that r squared equals x squared plus y squared. So real quick, we're going to look at the graph, just the rectangular graph of y equals 5. So this is what we know. We know that y equals r sine theta. And so y equals 5 can be written as r sine theta equals 5, right? So r equals 5 over sine theta, right? Alright, so we're just going to look at what that looks like when we graph that in Mathematica. So if those two graphs looked similar, it's because they were the same graph. So now we understand how to graph a horizontal line. And real quick, we're going to take a look at a vertical line. So we all know what the graph x equals 3 looks like. So once again, this is what we know. We know that x equals r cosine theta. So x equals 3 is the same thing as r cosine theta equals 3. So r equals 3 over cosine theta. And so we're going to look at Mathematica and see what they get. The last line that we're going to learn how to graph is the oblique line, which is the hardest of all the lines to graph in polar. But it's still not that hard. So, let's derive! We know that y equals mx plus b, and we know that y is r sine theta and x is r cosine theta. Therefore, r sine theta equals m times r cosine theta plus b. So we move all the r's to one side to get r sine theta minus m times r cosine theta is b, and then we take out the r. So it's r times sine theta minus m cosine theta equals b, for a grand finale of r equals b over sine theta minus m times cosine theta, where b is the y-intercept and m is the slope, just like in rectangular. Alright, so we're gonna check this out. So that's basically lines. They're really easy to distinguish, and there's nothing really tricky about the equations. So yeah, they're just pretty quick and basic. So we're going to move on to limicons. And you're going to have a homework paper where you're going to graph like a million limicons. And it's homework 20, you know, on the parametric and polar ones. So this is it. I found it. And there's about 4 million different graphs of limicons. And there's, you know, lines and other stuff thrown in there, but it's mostly limicons. So, yeah, you're going to get really sad. But it's okay, because, you know, like, I thought it was kind of hard at first, and then after that homework paper, it was just, like, the easiest thing I've ever done in my life. So, oh, by the way, this is all of my BC homework. And that one, too. So, that is it all. So if anyone needs it, I still have it. Alright, so that was super fun, and now we're going to move on to limicons, right? And so these are the two basic equations that you're going to need to know that will be the tip-off that it's a limicon. So we have r equals a plus or minus b times cosine theta, or basically r equals a plus or minus b times sine theta. And so there's 4 different kinds of limicons, and this is how you tell them apart. So the first is a loop, and a loop occurs if a over b is less than 1. And so that is what the picture of the loop will look like when you graph it. And I remember this one because loop has 2 O's in it, and if a over b is less than 1, that means it's pretty close to 0, and the O's, look a lot like zeros. So that is a loop. 2 is the cardioid, which happens if a over b equals 1. And so that is what it, right there, that's what a cardioid looks like. And so it doesn't like complete the loop, it kind of just like bounces. And so I remember this one because the word cardioid reminds me of cardiac, which is your heart, and you only have one heart, and the graph kind of looks like a heart. Kind of. So yeah, that's a cardioid. A over b equals 1. The third kind of limicon is dimpled. And so dimpled happens, it's kind of hard to see because this blue marker is not very good, but a over b is between 1 and 2. And dimpled kind of looks a little bit like cardioid, but it is different, and there's no memory device for dimpled limicons. So you just know this one. And finally, the last of the limicons is the convex limicon, which occurs when a over b is greater than 2, and that is the graph, and although it may look like a circle, it is not a circle, so don't mistake it for a circle. And I remember convex because, how do I remember convex? Oh yeah, it is the fullest looking of the limicons. It looks the fullest, like close to a circle, but it's not. But if you had 2 cupcakes, you would be full. Like greater than 2, you know? But if you had no cupcakes, you would be sad and hungry and lonely and empty, most importantly. You wouldn't be full like the convex graph is. So, yes. Now we're going to look at the graphs of all the limicons. First, we're going to look at a loop, and so we'll use the equation r equals 1 plus 2 sine theta, where so a is 1 and b is 2, so 1 over 2 is less than 1. So we have a loop. And so the easiest way to graph this, we have to find our points, which means we have to make a table of the thetas and solve for r using our equation 1 equals 2 sine theta. So now all I do is simply plot these points on the polar coordinate system from 0 to 2 pi. And we're going to be doing this a lot. So instead of telling you that we're going to be plotting these points on the polar coordinate plane between every single time that we find points in a table, in the future, we're just going to show you the table and then we're going to show you the graph. But this time I'll say it. Now that we have found our points, we're going to plot these points on the polar coordinate plane. So, okay, the next one we're plotting is r equals 2 plus 2 cosine theta. So we know that a is 2 and b is 2. So 2 over 2 is 1. And so this is going to be a cardioid. So once again, we're going to make our table using our thetas to find our r's, and then we're going to plot our r's on the polar coordinate plane. Thirdly, our equation is r equals 4 plus 3 cosine theta. So a is 4, b is 3. So 4/3 is between 1 and 2, so this is going to be dimpled. So let's make our table and graph our points. Alright, so we changed marker color because orange rules. And so this next equation, r equals 3 minus cosine theta. A is 3, b is 1, 3 over 1 is bigger than 2. And so this is going to be convex, which is close to a circle, but not quite. Aren't limb sounds the funnest? So yeah, now we're going to look at lemniscates. And I remember this because ice skaters skate in figure eights, or infinities, for those of you who didn't make that correlation. Okay, so for lemniscates, this is the basic layout that's going to trigger that thing in your mind that says, hey, this polar graph is a lemniscate. So that is r squared equals plus or minus a squared times cosine theta, or r squared equals plus or minus a squared times sine theta, which is most commonly seen as r equals the square root of a times cosine of 2 theta, or r equals a times sine 2 theta. So yeah, that's what the lemniscate formula is. And so now we're going to look at some examples. First one we're going to look at is r equals 3 times cosine of 2 theta. So, you know, we're going to take our thetas and put them into the table to find our r's, and then we're going to plot our r's on the polar coordinate plane. That was beautiful. And so we saw that it was kind of like an infinity going over the x-axis, which looking back we should have seen coming, because cosine we know correlates with x in we're going from rectangular to polar. So yeah, that makes perfect sense. So now we're going to look at one with y in it, or sine, sorry. And so r equals 4 sine of 2 theta. And so we're going to make our table and then plot our points, and there's something coming up that you're not going to see coming. Whoa. So I know what you're thinking. You're feeling deceived because you thought that that was going to go vertically, and I did too, but it went between the first and the third quadrant, and I'm sure there is a great explanation for that. But this video is already exceeding the time limit, so we're just not going to go into it. And instead, we're going to take a look at polar roses.
But did you know that when it snows, my eyes become larger? The light that you shine can't be seen. Yeah, I can read to a kiss from the rose on the way. Ooh, the more I get of you, stranger to feel.
So if you're wondering what the reason that Kiss from a Rose by Seal came into the video, there isn't really one, aside from the fact that it mentions the word rose, which is what we're looking at now. We are looking at polar roses. And so these are the equations and fun facts about polar roses that you're going to need to know. This is a tulip, but it looks like a rose, but my mom only grows tulips. Okay, so we have r equals a times cosine of b theta, or r equals a times sine of b theta. And so a is the size of the petals, and b times 2 is the number of petals that there's going to be. This is for the most part. So, yep, it's going to make a lot more sense when we graph that. We're going to look at r equals 5 times cosine of 2 theta, and usually for polar roses you have to plot a lot of points before you can kind of get the gist of where it's going, how it's going. you know, all that jazz. So we're going to take a look at the table, then we're going to take a look at the graph, and then we're going to come back here and we're going to talk about what we saw. So for those of you who are still watching, you probably noticed that that polar rose was like 4 petals, which was cool because B was 2, and 2B is the number of petals, which is 4, which means Mathematica complies with what I'm telling you. And also, you probably noticed that the petals went from the origin out 5, which was cool because the equation was r equals 5 cosine 2 theta, so A was 5, so the size of the petals was 5. So, yeah. So now we are at our last set of polar equations. Yay! So that is spirals. Like a spiral, you know? Boom. And so we're going to look at 3 different kinds of spirals, but we're only going to look at 2 because, see, there's Archimedes, logarithmic, and parabolic. That's probably how you say it. Parabolic. But I've looked for a long time for a good example of a logarithmic spiral, and there is none. And the one I used on my study guide is one I found offline, which is a bad idea. But it's just really confusing, and I would not have anything interesting to say about it like I do have things to say about all my other interesting graphs. So we're gonna skip the logarithmic. But we can talk about like its formula, but it's not gonna be on the AP exam. It never is. So yeah, we're just gonna skip that one. But first we're gonna look at Archimedes. And so, yep, Archimedes, the equation is r equals a times theta. So we're gonna look at r equals 4 theta. Well, that was wicked cool. You know, spirals are awesome. And so now we're just gonna take a real quick second to talk about logarithmic spirals, which are also awesome, but I don't know a lot about. But all I do know about them is that if you plot the line y equals x on it, which is this line, all of these angles that intersect the spiral are the same. And I don't know why or how, and this is not drawn to scale, but yeah, that is what I know about logarithmic spirals. Well, lastly, we're going to look at parabolic spirals, and so the basic formula for those are r equals a of theta. And so we're going to look, r equals a square root theta. Don't forget the square root. So we're going to take a look at r equals 2 square root theta. Yeah, so that was the parabolic spiral. And that is all of the polar equations that you are ever going to need to know, ever. And there will be variations of them, I'm sure, but if you ever, need to go back to basics, just come here and rewatch this really interesting video. And I'm really sorry if it didn't keep you interested. Like, I tried to keep it interesting, but yeah. It's kind of hard, and I thought maybe these glasses, these aren't real glasses. I thought maybe they would, like, keep you intrigued with, like, what's behind the glasses, But they were sunglasses, but I popped out the frames to make me look intelligent, which is stereotypical and probably wrong, but okay. Well, thank you very much for watching my video blog about polar equations, and I hope you have a really good day. And I hope that Calc BC is going really awesome, which it probably is, because Calc BC is awesome. Have a wonderful day!